All right, welcome to our second video of electron configuration. In this, we will actually talk about how to do electron configuration. If you are missing terms like orbitals or you're looking for the first part of these notes, there is another video. Feel free to watch that, but this one we are showing you how to do electron configuration. Now, there are three types of electron configurations. The first, most common, is the full electron configuration. This is where we list every single electron that exists in an atom or element or whatever we're doing. And these notations are actually quite important. The 1 means energy level 1, S means S-shaped orbital, and 2 is how many electrons are in them. Typically, S's will have 2's after them, P's have 6, D's 10, F's 14, except maybe the last one if we don't quite fill it. But we read this as 1s2, 2s2, not 1s squared, for example. And this order comes from this chart. Another type is a noble gas configuration. This is where we realize that all atoms will have the same electron configuration, at least of the previous elements, just maybe add an extra electron. So we kind of only write electron configurations after the most recent noble gas. So this full electron configuration is shortened to this. We put the Roman numeral in brackets and then say it's the same as neon, just add these couple extra electrons. That's kind of what we're saying. And an orbital diagram is our third kind. This is where we actually draw where the electrons are located in addition to their spin. This goes back to Hund's rule, where every one has to have an up before any can have a down. I'm not really sure why it did this, but those shouldn't be there. So, for example, this was drawn correctly because we should not put an arrow like that. You have to fill every orbital of the same energy level and shape before any of them have a down. All right, let's figure out how to do this. First part is you find your starting place. If it's the full configuration, you're just starting at the beginning, which is 1s. If it's noble gas, you're starting after the p orbital that has the energy level equal to the period the most recent noble gas is in. For example, on a periodic table, neon is in the actual second row, which means neon is going to be in 2p. So we're starting after 2p, which is 3s. And you just find whatever the most recent noble gas is, figure out what row it's in, that's the p block that we're starting after. On that arrow chart, just go to the next orbital, which will always be some kind of an S, and that's where we start. I recommend you pausing real quick, taking time to figure out why neon is 2p, or for example, krypton is in 4p, which means we'll start in 5s. So take a bit to figure out that, because that is probably the hardest part of noble gas configuration. It's not that hard, but it's a hard part to figure it out. So, yeah. I'm going to assume that you did pause and figured out how to get those orbitals. So we're going to move on now to determining the number of electrons. In the full configuration, it's just this. Take the atomic number of whatever compound you're dealing with and subtract any charge you may have. If it's noble gas, you're still doing that same thing as before for the full, but you're going to subtract the atomic number of the most recent noble gas, because we're only adding the electrons that are after the noble gas. So, for example, I don't know, arsenic has 33 electrons, but the most recent one is argon, which has 18. So that means that if we were doing the full electron configuration, we would use this one. For noble gas, it'll be 33 minus 18, which is 15. And arsenic didn't have a charge, so we didn't do anything with that. All right. Now we start placing electrons. We go back to that arrow chart that we showed before, and you just kind of follow that order and add electrons as you need. Keep in mind that 2 electrons go in S, 6 in P, 10 in D, and 14 in F orbitals. All right, so now we're going to do the electron configuration of selenium, which has an atomic number of 34. So let's go ahead and write the chart, but I will tell you I'm not going to do this for the rest. You have these in your notes, or if not, just go on a previous slide, write this chart down. I don't want to keep writing this every time. Hopefully you don't either. Now, my hope, though, is that you can do this, and you're thinking, yeah, I can do this really easily. I don't even need to write it down. But it is a very good practice to at least every set of homework problems, write the chart somewhere in your paper. That way you've got it written, you're kind of, using it, you've got it, it's still in your memory. Anyways, so selenium. First one is 1s, 2, and that gets us 32 electrons left. 34 minus 2. Next one's 2s, 2. Then we have 2p6, which leaves us 24. And I'm just following the arrow, by the way, because, 1s, 2s, 2p. Now we're down to 3s. I'm actually going to pause it real quick. Well, I'm just going to talk a bit. Try and keep going farther with this. You've seen an idea how I've done this. And you know that there's 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. But take a bit of time to try and finish this yourself. Again, you learn better by practicing. So I'm going to pause, let you try it, and then I'll finish it. All right, so I'm hoping you've tried it. So let's keep going. We have 3p6. Get you 16. We have 4s2. By the way, we keep going until this now 14 number gets 0. And if that fills an orbital when we're done, cool. We just keep filling orbitals until we're done. We have 3d, 10. This gets us 4. And our last one, for example, is 4p. Now, p can hold 6, but we only have 4. So this is going to be 4p4. Get you 0. And to kind of summarize this information, the answer I'd be looking for would be something like this. 2, 3p, 6, 4s2, 3d10, 4p4. So this is actually going to be the answer that we're using as, well, basically, I'm sorry. That was supposed to be a highlighter. That just really didn't work. But anyways, this answer down here is what we're looking for. So, as in not all the work and stuff up above. All right. Noble gas configuration of tungsten. The most recent noble gas to tungsten is xenon. Ah. Why are you not undoing? That's really weird. So the most recent noble gas is xenon, which has an atomic number of 54. Tungsten has an atomic number of 74, which means we have 20 electrons we need to place. Again, 74 minus 54. Xenon is in the 5th row, so that means it's in 5p. What comes after 5p is 6s, so that is where we're going to start. So xenon, now we have 6s, which can hold 2. After 6s comes 4f, which can hold 14. And then we finish in 5d with 4. And that is our noble gas configuration. Saves you a lot of time. Remember though, figure out where you're starting, which is right after 5p, so 6s. Figure out how many electrons you're going to have, and just start placing them. Keep following the chart. Finally, orbital diagram for vanadium. Vanadium has 23. Orbital diagrams always are full electron configuration, so we are starting at 1s. So we're going to draw 1s2, kind of make our configuration. So 21, 15, 3s. Wow, what am I doing? So 1s2, 2s2. Try and leave a little bit of space above it and between them. 2p6. And 3s2. 3p6. 4s2. 3d3. And then for every s orbital, we draw one line above it. P's, we draw 3. This goes back to last video. And D's, we draw 5. And now we start placing arrows. All my s orbitals, if they have a 2, just put up and down. If they don't have 2, they're going to just have 1, so just put a 1. Then for all my p's and everything else, we do everything needs an up before they have a down. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then 1, 2, 3. Now, yes, we have a few orbitals that are empty. That's fine. We can hold 10. We don't have to hold 10. So that is our final actual answer for the orbital diagram for vanadium. Just that whole thing with all the arrows. So yeah, there you go. And thanks for watching. Have a great time. Again, feel free to watch this video as much as you want. Let me know if you have questions in class. And if I don't actually know you in person, well, God loves you and have a wonderful night.